So this week we're going to start looking at systems of linear differential equations, and hopefully you're going to find that there are many of the things that we've covered in the previous few weeks that will be useful when we're looking at these. So we're going to use a lot of techniques that we've already seen in slightly different ways in order to solve these systems. So why might we want to do this? Well, right way back in the first lecture I gave you an example of trying to model an ecosystem that consists of Canadian lynx and snowshoe hares, a predator-prey situation, where we basically put together two differential equations which modeled the behavior, the population behavior of the two species. So we said, well, okay, if we look at how the change in population of the hares behaves over time, if there are lots of hares, then there will be a term that seeks to increase the number of hares because they get to reproduce. On the other hand, if there are quite a lot of lynx and there are a fair number of hares, then they interact, and obviously when a hare and a lynx interacts, then probably not going to end up so well for the hare, so we get a term which subtracts, which tends to decrease the rate of change of our hare population. And so we have a differential equation that describes how the hare population changes over time. And similarly, we put together a differential equation that describes how the lynx population changes over time. And the thing is, these two differential equations are linked together. We can't just solve one because each one contains the variables from the other. So our equation for our hares, dh by dt, has our hare function in there, but it also has the lynx function in there. And similarly, our equation for our lynxes, so remember each of these is a function of time. Our lynx equation also has a factor dependent on the function that governs the hare's behavior. So we have to solve these simultaneously. You've solved plenty of simultaneous equations before, so we're going to look at techniques for that when we have a differential equation that we need to solve simultaneously. You will find, if you go into any kind of quantitative discipline, whether it's physics or ecology or epidemiology, you get systems of differential equations. Whenever you have two things that you might want to monitor that are changing over time, that are somehow linked together, you're going to get a system of differential equations. So that is one reason why you might want to be able to solve systems. Another reason is that we'll see very shortly, you can often take a higher order differential equation, like a second order differential equation, and turn it into a system of lower order differential equations. So it might be that while it's tough to solve the higher order DE, it's easier to solve the system of lower order DEs. So that's another reason we use this technique. One thing that we are going to be using quite a lot of is matrices. So if you're feeling hazy about matrices, if you haven't done anything with matrices, then please go and have a read of the appendix of the textbook. I'll put a copy on Canvas and just work through some of those exercises and get familiar. I will discuss a little bit about eigenvalues and eigenvectors, but it would be helpful if you just kind of read through the basics of matrices to remind yourself, and then read through on eigenvalues and eigenvectors as well. Okay, so let's get started. So we're just going to set up some of the terminology. So if we're going to start by thinking about first order systems of ODEs. So we're thinking about systems of first order differential equations. And we have what's called a standard form that we can write them in, where we write, so we've got n different functions of time, x1 labeled all the way through to xn. And each equation we're going to have the dx1 by dt, so the dx by dt term on the left, and then we put everything else on the right, and that's called standard form. So if we want to have a look at an example, here's an example where we have two variables. So we have x1 of t and x2 of t, and we're going to say, for example, that our first differential equation would be x1 so I'm going to actually use slightly different notation. I'm going to use x1 of t is equal to, this is the f1 that we'll use, so minus kb x1 minus ke x1 plus ka x2 plus g of t, and our x2 of t, its derivative will be kb x1 minus ka x2. And you'll notice that in this system, in our x1 equation we have x1s, but we also have an x2, and in our x2 equation we've got an x1 and also an x2. So they have to be solved simultaneously. The other thing that you will notice is that we have in our x1's equation we've got a g of t, so we have a term that depends explicitly on t, so that makes this one non-homogeneous, whereas in our x2 equation over here this is homogeneous because we don't have a term that depends explicitly on t. So the same terminology that we used for individual differential equations applies over here. What we will often end up doing if we have a system like we have over here is we are going to define a vector-valued function that has as its components each of the functions. So if I was to write out this one over here, I would call this x of t, and I'm using the arrow overhead to represent a vector because I can't do boldface nicely when I'm writing. So here we would have x of t is equal to, x1 of t, x2 of t, and similarly we would write that our f of x t is equal to f1 f2, and I should put in those bits over here, I'm just being a bit lazy. So I will, when I'm writing, tend to make it explicit that x and f are column vectors, but often in textbooks you'll find them written like this because it's just easier typographically, but they are vectors. And usually when we've got a system of ODEs like we have over here, we'll have some initial conditions. So for each, because we're first order, so for each of our different variables we will have an initial condition. And we could write that in vector form like so. Okay. So a little more terminology. Just as we've been talking about individual differential equations being linear or nonlinear, we can do the same thing with systems. If it's the case that the right-hand side of our first order differential equation is linear, so it looks something like this, and every single one of our DEs in our system is linear, then we say that the whole system is linear. And if it is the case that each of the individual equations is homogeneous, then the entire system is homogeneous. But if you have even one that's non-homogeneous, then the whole system is non-homogeneous. So we can just do a quick check here. If we want to just make sure that we're happy with how things look. So here we have a system of two differential equations, and we've got two functions that we're looking for. We've got x1 and x2. And the question is, we want to verify that it's linear, so we verify that it has this form over here. So our f1 is of x1, x2, t is equal to tx1 minus 3x2 plus t squared. And our f2 of x1, x2, t is equal to minus sine of t x1 plus 3t x2 minus t. And notice that in order to be linear, what we need is for the coefficient of each of our functions to be just a function of t, and for our functions themselves to only ever appear as themselves, so never squared or rooted or anything like that. So let's just do a quick check. If we have a look at f1, then x1 in this term appears by itself, so that's fine, and its coefficient is just a function of t, so that's okay. Next term, x2 appears by itself, so that's fine, and minus 3 is just a constant, so that's fine. And finally we're allowed to have one term which just depends on t in any shape or form, which we've got over here, so that's fine. Good, okay, so that one is definitely linear. Looking at our f2, again, we can check each term that has an x in it. The x just appears by itself, so that's fine. This is just a function of t, so that's okay. That's just a function of t, so that's okay. And here we've got a function of t all by itself. So in this case, these two would be non-homogeneous because we have, in each case, a term that is just dependent on t. All right. So as we saw when we were dealing with just individual differential equations, another thing that we think about is whether the coefficients of each of the terms are constant or variable. Same thing happens here. So constant coefficient if the coefficient of every term in every term is constant, variable coefficient if not. So if we have a look at our example here, this is going to definitely be a variable coefficient because we've got variables here, variables here, variables here. Okay. So we are going to mostly focus on solving systems of first order linear constant coefficient ODEs, and today we're specifically going to look at the homogeneous case. So just like we did when we looked at single differential equations, we start with the homogeneous case and then we have a look at the non-homogeneous case. So just for a moment, let's step away from solving those, and you remember that I mentioned at the start of this video that we can sometimes convert second order or higher order differential equations into systems of lower order differential equations. So here's an example. Here is our classic damped harmonic oscillator, and it's driven, and we're going to turn this single differential equation into two lower order, in this case two first order differential equations. How do we do this? Well, we firstly define a new variable. So we're going to let x of t be, well, I'm going to call this x1 of t, and I'm going to let that be equal to u of t. And then I'm going to define a new variable, x2 of t, and I'm going to let that be equal to the derivative of u of t. Okay? So now I'm going to take the derivative of both of those. So I've got the derivative of x1 of t is just going to be the derivative of u of t. So in fact this is, which by this definition that we've just got over here, is going to be equal to x2 of t. So far I haven't done anything particularly interesting, but I'm also going to take the derivative of x2 of t, which will be the second derivative of u of t. And I'm going to use these two definitions to rewrite this differential equation. So let's rewrite this one in terms of x1 and x2 and their derivatives. So I've got m u double dashed of t, and u double dashed of t is the same as the first derivative of x2 of t. So I've got m u2 dashed, got m x2 dashed of t plus, So u dashed of t is x2 plus x2 of t times c plus k times u of t, which is just x1. And that's going to be f of t. So if I divide through by m and do a reorganization so that I just have my x2 dashed of t on the left and everything else on the right, what we get is x2 dashed of t is equal to minus c over m x2 of t minus k over m x1 of t plus f of t. And if I combine that with this equation over here, and maybe move these, so I'm actually going to move this one underneath so that you can see it neatly. Suddenly I've got two differential equations that should be an F there. So I've got two differential equations, but they're both first order and they're both linear. So although we know how to solve second order differential equations like this, this shows that you could instead turn that second order differential equation into two first order differential equations and solve them simultaneously. So we'll look at techniques for doing that as well. So the key trick, what we did over here, was we had one variable, our x1, which was just the initial variable that we were looking at originally in the single ODE. And then the second thing that we did was we defined a second variable, which was the first derivative of the original variable. And if you were looking at a third order differential equation, then you could define a third new variable, which was the second derivative of the original variable. And then you'd find that you have a system of three differential equations. So you could really simplify things down. Okay, so before we dive into actual techniques, the question that we've always asked ourselves every time we're looking at a differential equation has been, can we actually find a solution, and is that solution unique? So we've done this for first order equations, we did this for second order equations, so we're going to ask the same question: if we have a first order system, can we find a solution, and is that solution unique? And we have a useful theorem. So if we have a system of dE's like the ones we've just seen, so dx1 by dt equals some stuff, dx2 by dt equals some stuff, and so on. If each of the right-hand sides, so the fk, is continuous and has continuous partial derivatives with respect to all variables in some region, then we can find a unique solution to the system. So really what this is saying is, if you have a look at the right-hand sides when you're written in standard form, and those functions are kind of well behaved over however many variables, so they're continuous over all variables and they have continuous partial derivatives. So if that's the case for each of the right-hand sides, then you'll be able to find a nice solution in some region. Things that you would need to be aware of, which we've already seen, is as soon as your right-hand sides get a little bit weird, so you have a Heaviside or Dirac delta, then this theorem doesn't apply and you have to use other techniques. So it's not the case that if you have a Heaviside or Dirac delta, you don't have a solution. It's just you can't guarantee that the solution exists. You have to use some other technique. So this is a nice theorem because it says we're not going to waste our time. If our things are well behaved, we should be able to find a solution. So let's learn how to do that. So the first thing we need to do is learn how to go from a whole system written out in excruciating detail as n different equations. That's really cumbersome and not helpful. So what we're going to do is learn to write this as a matrix equation and then we're going to be able to use all of matrix algebra to help us. So I've just written out a system of first order constant linear ODEs here. So here's the equation that governs x1. So dx1 by dt, and you'll notice I've got my constant coefficients. It's definitely linear, and I'm keeping it non-homogeneous, although later on we're just going to deal with the homogeneous case first. So I've got n of these equations, and I've cunningly labeled each of the coefficients. So you'll notice that the first index refers to whichever equation we're dealing with. The second one refers to whichever variable we're dealing with. So what I'm going to do is I'm going to let this x, this is a vector x, consist of a column vector with n entries, where each entry is one of the independent variables that we're interested in. Okay? And similarly, I'm going to let vector b be a column vector which has as its entries each of these explicitly time-dependent terms. And then finally, I'm going to let A be the matrix that I construct by pulling out all of these coefficients in order. So those are the coefficients from my first equation, coefficients from my second equation, and so on. So this is an n by n. Our x of t is an n by, it's an n by 1, and our b is an n by 1. And using this formalism, we can do something really kind of cunning. We can rewrite star. So star was this whole crazy mess over here of all these. We can rewrite it very simply as a matrix equation. So that's the derivative of this vector x. So that says component-wise take the derivative is equal to A, so that's this matrix here, times our vector x of t. So that's quite a useful and very compact notation. If you're feeling a bit weirded out by this, then I suggest that you actually go and multiply out a times x and convince yourself that if you do that, you end up with this right-hand side over here. And, oh, I should have, where are we? And I should have a plus a b of t for the moment. Okay, because I've got these b's sitting over here. So this looks nice and simple, and it gives us a kind of a quick way of seeing if our b of t over here is equal to 0, then the system is homogeneous, but otherwise it's non-homogeneous. Okay, and now that we've written this in matrix form, we get to use all of matrix algebra in order to help us solve this equation. So let's just practice writing things as a matrix equation. So we're going to let our x, which for the moment we're just going to carry on explicitly writing as a function of t, is going to be x1 of t, x2 of t. And our a here will be 3, 2, 1 minus 5. And then we can write this as derivative of x of t is equal to ax of t. Okay, so let's look at solving an equation like the one we've just seen, which is a homogeneous system of DEs. And we're going to be inspired by the work that we already did on solving first-order linear differential equations. We're going to try a solution and see what we find. So we're looking at equations like this. I'm usually going to write this as x prime of t, just because notation here, I find that a little bit easier, but whether you use the prime or the dot, it means dx by dt, and because this x is a vector, it means take the derivative of each component with respect to time. And the thing that we're going to try is, if you think about when we tried our ansatz, we looked at single differential equations of this form, and we tried a solution of the form e to the at. And we're going to do something similar here, where for things of this form over here, where we're looking at our vector equation, we're going to try a solution, so this is a vector, of the form e to the alpha t, e to the lambda t. So this is a scalar, and it's a scalar function of t. Times by some vector v, and this is going to be a constant. So we're comparing this with the solutions that we tried of the form e to the at times c. So we're doing something similar here. Just foreshadowing what we might get to next week is actually, if we were doing exactly the same thing, we would actually try something of the form e to the matrix A times t times v. But we haven't yet defined what this would actually mean. So we can define e raised to the power of a matrix, but we haven't done that yet, and that takes a little bit of work. So for the moment, we are going to stick with e to the lambda t, where lambda is a scalar, and we can actually solve using that. So remember what we did when we had a single differential equation and we were trying an ansatz. We just differentiated our ansatz, our guess, and figured out what values of the constants in the ansatz needed to be true in order for our ansatz to fulfill the dE. So we're going to do exactly the same thing over here. We are going to say, okay, well, we want our x of t equal to e to the lambda t times v to solve. Remember, we're trying to solve this dE. So let's differentiate. So remember, we're differentiating each component, but we're just going to write this as a vector. So we're going to get x dashed of t is equal to, and now remember, this is a function of t, our v is a constant. So all our v's will just come along for the ride. So the only thing we have to worry about is differentiating this e to the lambda t, which is just a function like we know, and the derivative is lambda e to the lambda t times v. Okay, so let's sub this into the dE that we want to find the solution to, which is this. So we've got lambda e to the lambda t times v must be equal to a times x, and this is our x over here, a e to the lambda t times v. So this should look sort of hauntingly familiar, except that we've got some vectors in here, but other than that we've got the same situation that we had before. Notice that we've got an e to the lambda t on both sides, and e to the lambda t is never 0, so we can divide through by e to the lambda t. So let's do that. So this funny symbol here means for all. So we end up with lambda times v must be equal to a times v. So if you've done much matrix algebra, you'll have seen this equation before, but if you haven't, it's quite interesting. So look at what this equation is saying. It's saying we've got some vector v, which is a constant vector, and if you multiply that vector by a, so you'll get some new vector, it's the same as multiplying that vector by some scalar constant. So it's kind of like saying you've got 2 times v must be equal to A times V, where A is some complicated matrix. And this is kind of an important thing within matrix algebra. If you have a situation where you have some vector V that belongs to a matrix A, and multiplying by A is the same as multiplying by lambda, then we call this vector V here an eigenvector of A, and this value over here is called an eigenvalue. One of the powerful things about knowing about eigenvectors and eigenvalues is computationally matrix multiplication is very expensive. So if you have a vector, if you have a matrix, and you know its eigenvectors, and you know its eigenvalues, then instead of having to multiply the vector by the matrix whenever you want to work out what that is, if you just multiply by the scalar, its eigenvalue, that's a lot quicker. So yeah, if this is new to you, please go and read a little bit more about these. So if we can find a lambda which makes this whole thing true, then our solution x for the lambda and the v will be a solution to our system of ODEs. So we're doing the same thing that we did for the single DEs, but now we're doing this for a vector equation, but it's exactly the same idea. So if we find lambda and v and make this true, then x is a solution. So how do we go about finding these eigenvalues and eigenvectors? Well, this is straight matrix algebra, linear algebra. So just to kind of give the terminology, if we have some matrix A, then, and this is important here, a non-zero n-dimensional vector is an eigenvector for A with associated eigenvalue if taking A times our eigenvector is the same as multiplying our eigenvector by the eigenvalue. Very important thing here, and we're going to use this fact a lot, is that V cannot be the zero vector. Because if V was the zero vector, well, this is always true. So we wouldn't be doing anything interesting. So we always declare that V is non-zero. All right, so how do we find eigenvectors and eigenvalues? Well, generally speaking, we ask a computer to do it for us, but we will do a little bit. We'll do this once, and it's pretty straightforward for a 2x2 matrix. For 3x3 or anything more than that, you definitely want to use a computer. So if we want to find the eigenvectors and the eigenvalues, the first thing that we're going to do is find the eigenvalues. And this is going to take a little bit of knowledge of matrices, but we can do it. So if we think about what is the equation that we want to solve. So if lambda and v are eigenval and eigenvector, then we know that A times v must be equal to lambda times v. And we can just matrix multiply this out so that we're going to get two equations that we can hopefully solve together. So we get v1 plus 3v2 is equal to lambda v1, so that's our first row, and 3v1 plus v2 is equal to lambda v2. And we can do a little bit of rewriting to get 1 minus lambda v1 plus 3v2 is equal to 0. And we've got 3v1 plus 1 minus lambda B2 is equal to 0. And now I'm going to rewrite this as a matrix equation, because we'll see something important, which is that we must have okay, so all I've done is a little bit of rewriting. So I've just rewritten this equation. But there's an important thing here, because we know that V can't be 0, because we've said it's an eigenvector, and eigenvectors are not allowed to be the 0 vector. So V can't be 0. And so we can deduce that this matrix over here can't be invertible. So we can't find some matrix which we can multiply over here, which will give us 1, because if we did, then this vector would be the 0 vector. So it must be that this can't be invertible. We can't find an inverse matrix. Okay, so hopefully you've talked a little bit about matrices and determinants. If you haven't, please go and read a little bit about this. But saying that a matrix can't be invertible means that the determinant of this matrix is not 0. Because if the determinant is 0, then if the determinant of a matrix is 0, then it's invertible. So similarly, the determinant is not 0, not invertible. Okay. What is the determinant? So our determinant again, please go and read up if this is hazy. For a 2x2, so I'm going to call this, let's just call this thing B. So our determinant of B is, for a 2x2, we just say we multiply the diagonal terms. So I've got 1 minus lambda, 1 minus lambda, and then we subtract off, multiplying the off diagonals. So we got minus 9. And we set this equal to 0. Sorry, I said means our determinant should be 0. I misspoke. So we calculate our determinant equal to 0, and we're solving for lambda over here. We've got what is called the characteristic equation that we're solving. And if you solve for this, you'll get lambda minus 4, lambda plus 2 is equal to 0. So we get lambda is equal to 4, or lambda is equal to minus 2. And I'm going to label this as lambda 1, and this is lambda 2. So there was a whole bunch of stuff that I've talked over very quickly and not in a lot of detail. If you haven't seen this before, as I say, please go and read the appendix. But basically, just to recap what we've done, we said, okay, if we want to find the eigenvalues and eigenvectors of this matrix over here, in order to be an eigenvalue and an eigenvector, this equation must be true. So I did a little bit of rewriting, and equivalently, it must be the case that this equation is true, where we've got this matrix multiplied by the vector must be equal to 0. But then our logic says, well, we've declared that we want this vector to be an eigenvector, so it can't be the 0 vector. So the only way that we can make this equation true is if we can't find an inverse for the matrix multiplying. Because if we could find an inverse, then we could just multiply both sides of that equation, and then we'd end up with v1, v2 on the left-hand side, and we'd have 0 on the right-hand side. And then our v would be 0, but we just said it can't be 0. So the only way to prevent that is to make sure that this matrix over here isn't invertible. But in order to not be invertible, it needs to be the case that the determinant is 0. So the determinant is a thing that you calculate from the matrix. And so in order to find the values of lambda, which ensure that we can't have an invertible matrix here, we solve this equation over here, and we'll find that there are actually 2 eigenvalues. So either 4 or minus 2 will solve our problem. So just to kind of abstract from the specific example and recap if you haven't seen it before, for a 2 by 2 matrix, which has entries A, B, C, D, the eigenvalues are the roots of the characteristic equation, which is given by this thing over here. So we just found that. Okay. Phew. So we have found the eigenvalues. Now we want to find the eigenvectors. So let's find the eigenvectors. So again, so let's have a look at, I'm going to look at for lambda 1. I'm going to look at lambda 1. Let's look at lambda 2 because I've done that one. Lambda 2. So we're going to find the eigenvectors that belong to this particular eigenvalue. What do we know is true? Well, if it's going to be an eigenvector, it has to satisfy the equation that we've just seen. So we have to have that 1, 3, 3, 1 times v is equal to our eigenvalue times v1, v2. Equivalently, writing in the form that we've seen up here, I've got 1 minus our eigenvalue and 1 minus our eigenvalue on the diagonal. You can use exactly the same reasoning that we did here. So you're going to have 1 plus 2, 3, 3, 1 plus 2, v1, v2 is equal to 0. And just to, let's make it like so. Okay, so again we've got two equations and 2 unknowns. Let's just write out the equations. So we've got 3v1 plus 3v2 is equal to 0. That's our first line, and our second line will also be 3v1 plus 3v2 is equal to 0. And you might look at this and go, well, that's a problem. We have 2 equations, but they're the same, so we can't find a unique solution. But that's exactly what we'd actually expect, because we wouldn't expect to find a unique eigenvector. If you have a look at the equation that we're satisfying for an eigenvector, if you had some v1 that's an eigenvector, if I looked at 2 times v1, that would also satisfy this equation, because you'd have, if you've got a v1 is equal to lambda v1, well, if I plug in a 2 times v1 is equal to lambda 2 times v2, the 2's will cancel, we've got the same equation. So 2 times v1 is also going to be an eigenvector. So we would expect that what we have actually is a family of eigenvectors that just all point in the same direction. So what we're going to do is find one specific one. And you can take your pick. So usually in a situation like this, I would just pick a simple value for v1, like 1, and then see what v2 should be equal to. So let's pick v1 is equal to 1, plug that in. If you plug that in, you get 3 plus 3v2 equals 0, so you must get that v2 is equal to minus 1. So v equal to 1 minus 1 is an eigenvector lambda 2 equal to minus 2. But there's no particular reason you could also, you had to pick 1, so you could also have picked 2, in which case you would have got v2 is minus 2, and then v equal to 2 minus 2, also an eigenvector. But the key thing here is just having one vector that is definitely an eigenvector. And so you will have solutions that look different but might actually be the same. So you can check for yourself that for lambda 1 equal to 4, an eigenvector is 1, 1. Okay, so this is just to give you a quick recap or possibly introduce you to the idea of finding eigenvalues and eigenvectors for matrices. If you've seen it before, fantastic. If you haven't seen it before, as you can tell, this has been very hasty, so please go and read the chapter, maybe do some examples, and just get comfortable with finding eigenvalues and eigenvectors, because we will be using them quite a lot. Okay, so that was a diversion. So it turns out that we do have quicker ways of finding the eigenvalues of a 2 by 2 matrix if we know the trace and the determinant. Now the trace is just the sum of the diagonal entries. And the determinant, we've seen the formula for that. That's the formula for a 2 by 2 matrix. If you're finding the determinant of a higher order, higher dimensional matrix, it's a bit more complicated. We're not really going to talk about that here. So if we want to find the eigenvalues of some matrix A, we need to find the trace and the determinant. So let's just have a look at a quick example. So let's look at the matrix minus 5, 3, 1, minus 3. Then our trace, which we're going to call T, is minus 8, and D, which is our determinant, it's going to be minus 5 times minus 3, so that's 15, minus 3 times 1, which is 3, so that's 12. And we can write down straight away lambda 1 is equal to minus 8 plus 8 squared, which is 64, whoops, minus 4 times 12, which is 48, all over 2, and if you simplify that, you get minus 2, and if you look at lambda 2, you can work out that's minus 6. So that gives you a quick way of finding out the eigenvalues. We could also work out the eigenvectors. If we look at lambda 1 equal to minus 2, let's just check. Then we're solving the equation. So we're looking at this. So we're solving, here we've got minus 5 minus minus 2, so that's minus 3, 3, 1, and then we've got, over here we've got our minus 3 minus minus 2, so that's going to give us minus 1. V1, V2 is equal to 0. And you can have a look and see, so you could solve this as two simultaneous equations, but if you want to see what vector you need to have in order to do this, so remember this is really 0, 0, we need to have minus 3 times V1 plus 3 times V2 is equal to 0. Well, the only thing that's really going to work here is something where V1 and V2 are the same. So for example, 1, 1 would be a solution. And similarly, if you have a look at lambda 2 equal to minus 6, then you're solving the equation minus 1, 3, V1, V2, 1, 3. We'll just double check that. It has to be equal to 0. Let's just have a check. So we've got minus 5 plus 6, so that's going to be a 1 and a 3, so that should not be a minus. And again, if you have a look at these, what values of v1 and v2 will make this true? Well, a simple option would be to take v1 equal to 3 or minus 3, so you could do 3 and minus 1, or minus 3 and 1. Those will be simple things that work. So this technique makes things a little bit quicker, and experience will help you finding the eigenvectors, but you can just solve using simultaneous equations like we did before. Okay, things to kind of know about. So I'm just putting this here, we will use this a little bit later. We can work out whether our eigenvalues are going to be real or imaginary, because if you look over here, our eigenvalues involve a square root of something. So you can imagine that there'll be situations where the square of our trace is smaller than 4 times the determinant, in which case we're going to get a negative sign under the square root, so we might get imaginary things. So we can use this trace determinant form to basically tell us about our eigenvalues. Will they be real? Will they be complex? So if our d is less than 0, then in this case both eigenvalues will be real, and you can work out for yourself why this is true. If our determinant lies between 0 and our trace squared over 4, then both eigenvalues are real and both have the same sign as t, either positive or either both positive or negative. And finally, if we're outside, so if our t squared over 4 is less than our determinant, then both eigenvalues are complex and they'll be conjugate. So at the moment I'm just telling you this stuff, but it is going to be relevant for when we look at our solutions. So our eigenvalues are going to play a huge role in what our solutions look like, in the same way that the roots of our characteristic equation played a big role in whether we had oscillatory or decaying solutions for our single DEs. Okay, so let's dive in and solve a linear system that looks like this. So conveniently, we have already solved part of the problem because we found the eigenvalues and the eigenvectors. So we just did that a moment ago. So we have our eigenvalues. So let's have, we had lambda 1 equal to minus 2. Okay, and at this point you might be saying, well, okay, how does that help us? This helps us because the whole reason we found our eigenvalues and our eigenvectors was because we said we wanted to find a solution of the form x is equal to e to the lambda t v. And in fact what we found is that if we take this pair, so minus 2 is our eigenvalue and this eigenvector, that will be a solution. But similarly, if we take this eigenvalue, our minus 6, with this eigenvector, that's also a solution. So for a fair amount of work, admittedly, we've in fact found 2 possible solutions. let's just write them out explicitly. So I've got a W1 where I've taken lambda 1 and the first eigenvector, and W2 is e to the minus 6 t minus 3, 1. So what we do is we say, well, if we want the most general solution, and remember we'd like to be able to solve, if we go all the way back to, where's our problem? Our problem has these initial conditions. We want to find a solution for any general initial conditions. We have two initial conditions, one for x1 and one for x2. So we would like to have a situation where we have some constants that we can play around with in order to find our solution for those initial conditions. So what we're going to do, which we've done plenty of times before, is combine these two specific solutions to form a general solution. So we get a general solution is going to be our x of t. Now remember we said that any multiple of either of these will also be a solution. We can go back and check for the homogeneous case. So let's make a linear combination of the two. So we get c1 e to the minus 2t 1 1 plus c2 e to the minus 6t minus 3 1. And this should be starting to look hauntingly familiar. We've been doing the same things before. And it shouldn't be a surprise if we think about why we've got two constants here. Think about what we're doing. We're finding two solutions. Well, we're finding solutions to two first-order differential equations. And when we find a solution to a differential equation, we are, in a sense, integrating. So when we integrate in order to get the solution for x1, we would get one constant. And when we integrate to find the solution to x2, we get another constant. So it shouldn't come as a big surprise, even though we've done something completely different that didn't involve any integration at all, that our solution ends up with two constants. Okay, so that should be okay. All right, so that's our general solution. Now we want to find the specific solution to include our initial conditions x1 at times t equals 0 is 1, x2 at times t equals 0 is to 3. So you plug that into our equation over here. So we should get that 1, 3 is equal to, so this is going to be c1 c1, because this term will be equal to 1, so it's c1 multiplying 1, 1, plus, and then we've got c2 times minus 3, so that's a minus 3 and a c1, sorry, a c2. And you can solve those simultaneously, so you can either solve them as vector equations or as the equation 1 is equal to c1 minus 3c2 and 3 is equal to c1 plus c2. If you solve those simultaneously, you'll find that you get c1 is equal to 2 and c2 is equal to 1. And so finally we can write down our specific solution for those particular initial conditions is this. And what we would read off, if we wanted to read off individual solutions, would be that x1 of t is equal to 2 e to the minus 2t minus 3 e to the minus 6t, and x2 of t is equal to 2 e to the minus 2t plus e to the minus 6t. Okay, So this is the general procedure for solving a system of first order homogeneous constant coefficient linear DEs. It's summarized over here reasonably straightforwardly. So you probably need to run through this a couple of times, but what we did was we just followed this procedure. So we wrote our system of DEs in this form over here. And it's important to do that because that means then you can find your vector A, your matrix A. And the very first step is always to find the eigenvalues and the corresponding eigenvectors for A. And the reason that you do that is because once you've got those eigenvectors and eigenvalues, then you can construct these W's where you use the eigenvalues and the eigenvectors, and each W that you construct will satisfy the differential equation. So you find a bunch of solutions. And since each of the W's that you find satisfies the DE, you can form a general solution, which is a linear combination of the W's. So what you do is you form your final solution is something of this form here. So each term in your general solution has a constant of its own, an e to the something t, where the something is one of the eigenvalues, multiplied by that eigenvalue's corresponding eigenvector. And you do it for each of the eigenvector pairs that you have. This is the case if your eigenvalues are distinct. So you can imagine, just like we had the case for repeated roots when we're looking at single differential equations, we had a different thing happening here, and same thing happens here. If your eigenvalues are the same, then we need to do something different. So everything here is if our eigenvalues are distinct. So you formed your general solution, then you plug in your initial conditions, find your values of C, and you're done. So this probably seems a bit crazy, but hopefully by the time you've been through it once or twice, you'll realize that we're really just doing almost exactly the same thing that we did for single linear differential equations. We just kind of tweaked it a little bit so that we can do the matrix option. Okay, so I hope that you gave this one a try. If you did, what you should have found was that the eigenvalues are complex. And the associated eigenvectors will look something like this. So your eigenvectors might be multiples of these, but they should look similar. And one of the things that you'll notice, just as we in previous cases, if you get complex eigenvalues, so complex roots, then you should find that your two eigenvalues are complex conjugates of each other. And similarly, the associated eigenvectors will be complex conjugates of each other. So if that didn't happen, go back and check your working. So once we find the eigenvalues and the eigenvectors, following our recipe over here, we just construct our general solution using these. So we get x of t is equal to c1 times our first eigenvalue times our first eigenvector plus c2 e to the minus 1 minus 2i, so complex conjugate, and another complex conjugate. So that's our general solution, and if you substitute in our initial condition, then you should find, and I'm going to let you do the working for this, that C1 is equal to I, and C2 is equal to minus I. And again, you'll have a situation where if you get a complex value for one of your constants, then the other one will be the complex conjugate. And there's a lot of beautiful maths around why this is always the case. Sadly, we can't go into that in this course, but it is lovely. So if we put this all together, we end up with this slightly monstrous looking thing here. And you're probably having the same feeling that you had sometimes when we were solving our second order DEs and we got things that really looked extremely complex for a situation which really should have a real solution. So if we go back and look at this differential system of differential equations here, there's nothing imaginary there. So why would we suddenly be having imaginary bits in our final solution? And we have exactly the same answer, which is that actually, with some cunning rewriting, x of t is real. There are no imaginary components. It's just the way that we've written things. So once again, you could leave things like this, but generally speaking, we would like a more easy to understand solution. So we're going to rewrite this in real form. And as usual, we apply to Euler. So let's have let's say, a real looking would be nicer. And once again, we're going to use Euler. So the two things that we want to do, we want to rewrite each of our e terms. So we're going to write e to the minus 1 plus 2it. It's going to be e to the minus t cos of 2t plus I sine of 2t, and the complex conjugate So if you do that and you do some rewriting, then you can get your x of t in this form here. So these x's are equivalent, but this is going to be something that's much easier to see what it looks like. So you can see straight away here that this is the kind of solution that we would expect for the sorts of differential equations we've been looking at. So we've got a decaying exponential with an oscillating component for both of our solutions. So a lot easier to see. And in fact, we can see where our eigenvalues and eigenvectors have become quite important, so particularly our eigenvectors, our eigenvalues. Remember, our eigenvalues were minus 1 plus or minus 2i, and they are really important within this solution because you'll notice that the minus 1 is present as our decay rate. So the real part of our eigenvalue is telling us how fast the exponential is decaying, and the imaginary part, our plus or minus, so here, well, our coefficient here of our 2 is telling us the angular frequency of the oscillatory part. So this is why it becomes quite important to think about our eigenvalues. So I talked a little bit about how we can tell about what we can tell about our eigenvalues based on the determinant and the trace. The reason we want to be able to do that is because the values of our eigenvalues tell us a huge amount about the nature of our solution. So even if you just found the eigenvalues without even going through putting together your solution, you can immediately tell stuff about your solution. So is it decaying or maybe exploding? And is it oscillating? If it's oscillating, how fast is it oscillating? So the eigenvalues are crucial. And this is they are playing the same role that the roots of the characteristic equation played when we were looking at individual differential equations. So a lot of this, there are a lot of parallels between these. So putting together what we've just seen, and this is an equivalent formulation. Remember, we had a form that said we know how to rewrite our solutions to be real appearing. This little theorem 6.2.1 does the same thing. So if you have, so for the 2 by 2 case with complex eigenvalues lambda 1 and lambda 2 with corresponding eigenvectors, then the real value general solution, so written to look real, will be like so. You could also use this form over here. So this is just kind of saying in a theorem what we just saw. So I would not expect you to solve a higher dimensional situation in a test or exam, but it's useful to see where these kinds of things might happen. So we might have, for example, something like this case over here. So now we're looking at two trolleys that are linked by springs, and we're trying to figure out what their motion would be like. So you can imagine there'd be a whole lot of jiggling around. If you moved one, it'll pull on the other, which will pull back, and there'll be a whole lot of crazy stuff. So you could model this using two second-order differential equations, because we've seen that to model something on a spring, you need a second-order differential equation, and you'd have one for each mass. So you'd have two second-order differential equations. And then you can use the same trick that we did to get the second order into two first order. In here, you take each second order and turn it into two first orders. So you would end up in a situation with four differential equations, four first order differential equations, in which case you would have a matrix A that is 4 by 4. But you can use all the techniques that we've been doing so far. In particular, you could plug it into MATLAB, so that little bit of code there tells MATLAB what A is, and then delightfully you can use the Eigen Command. If you use it with two outputs, then the first output will give you the eigenvectors. So you'll notice here that we've got four, so I think we haven't seen all of it, but we've got 4 eigenvectors, and here it's a 4 by 4. And so each column, so there should be some more columns over here, each column is one of the eigenvectors, and D will give you the eigenvalues along the diagonal. So you would have 4 more like that, and they correspond, first eigenvalue corresponds to first eigenvector, and so on. So that's pretty useful. So using MATLAB, you could solve that part of the problem quite quickly. Again, you would construct a general solution. So here you've got 4 eigenvalues, 4 eigenvectors. So in your general solution, you'd have 4 terms. So you have C1 e to the first eigenvalue t times your first eigenvector plus C2 e to the blah 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 times your second eigenvector plus C3. So you'd have 4 terms, and they would be complex looking, so you could play the same game with Euler, and eventually you could do some rewriting and get a general solution that looks something like this. So in this particular case, you don't have decaying exponentials, you just have oscillatory terms. And just to give you an idea, when you put these together, so remember we originally had 2 second order differential equations. We turned it into 3 first order, but we're particularly interested in the variables for those first 2. And if we plot, so where they've been done here, these 2 are the solutions to the motion for each of these. Plot that, and what you get over here is oscillatory solutions. which is kind of what you might expect if you think about the system that we had, where we've got two little masses joined together. There's no friction, they're just bouncing each other, they just oscillate freely. So again, I wouldn't expect you to be able to do something like this in a test or exam, or possibly even in a tutorial, but I wanted to show you how the process might go for systems of more than just two DEs. You use exactly the same process. So the one case that we have left to deal with is what happens if we have what's called a defective matrix. What do we mean by defective? We just mean that the eigenvalues are not distinct, so the roots of the characteristic equation for the matrix are the same, and when you try and find the eigenvectors, you can't get distinct eigenvectors. So if you try to do it, you'll find that you only get one eigenvector instead of the two distinct ones that you would need for each of the two eigenvalues. And in this case, the matrix is said to be defective, and the problem with that is that you end up with only a single solution, whereas you really need two solutions if you're talking about the 2 by 2 case, which you can form a linear combination of to give a general solution. We've already seen this situation when we were looking at our harmonic oscillators, and we try pretty much a similar approach to solving this one. I'm not going to go into a lot of detail, but essentially we have the first part of our solution looks like the kind of thing that we've tried before, this e to the lambda t times v. But because we've only got the one lambda, we only get one of these. And the second, so then we try a solution that looks like e to the lambda t times v1 plus t times an eigenvector. And you can work through to see that this actually works. It's slightly more cumbersome than we've seen before. But what this kind of boils down to is saying that even in the case where you have eigenvalues that are the same and indistinct eigenvectors, you can still find a general solution to your system of DEs, and it will look like this. So your lambdas and your v's are the eigenvector and eigenvalue that you found. The v1 is slightly strange. It satisfies this equation over here, and it's beyond the scope of this course, but it can be proved that in fact you can find infinitely many vectors that always satisfy that equation. So we might do an example in a tutorial, but it is quite a lengthy procedure, so we wouldn't do it in a test or exam. But I needed to kind of include it here to say we've handled all the cases. So no matter what matrix you have in a situation like this, you can always find a general solution, assuming that you've got your coefficients or constant coefficients. Yeah. So what have we done today? Today we've had a look at mostly 2 by 2, but it's fully generalizable. So systems of constant coefficient homogeneous linear differential equations, and we figured out how to solve them. And it's mostly looking very similar to just solving, for example, second order linear differential equations by themselves. What do we have left to do? Next week we need to talk about the non-homogeneous case. So how do we handle that? And if we have a little bit of time, we'll talk about the matrix exponential, which I mentioned briefly. But for this week, please get comfortable finding eigenvalues, finding eigenvectors, and then putting them together to solve systems of DEs.